professor at the Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are discussing problems on extended surfaces, fins, and Bayet and Fourier number in heat and mass transfer subject. The heat transfer from hard surface to the surrounding by using convection process can be determined by using the relations Q is equal to HA into Ts minus Tf. Here the convection process is only applicable for transfer of heat from the liquid to the solid surfaces or from the solid surface to the liquid now, where H is representing the coefficient of convective heat transfer, A the surface area, Ts is representing, here we are taking the temperature is transferring from the solid to the liquid, Ts is representing the temperature of the solid surface, and Tf is representing the liquid temperature. It is obvious from that equations, in order to increase the rate of heat transfer for that particular combination, it should be high, or area of the cross section is more, or the difference of temperature Ts minus T should be more now. But there is a limitation of increasing difference of Ts and Tf, because we cannot heat that object, that is the surface of the solid, at a certain temperature, and Tf is the fluid temperature, we cannot decrease it now. Okay, depending on environment conditions, that is fixed now. Hence, Ts and Tf, it is not desirable to increase its values. H is known as here the property of the liquid and surface now. It is a coefficient of heat transfer by using convection mode. It cannot be increased now. Only the option is we can increase the area of the surface now. This area of the surface can be increased by inserting certain projections, what we are calling, these are protrusions and not solid surface. These projections are called fins or the spines. Because of this material, the surface area is increased considerably. Generally, these projections are made up of materials which are having high conductivity, such as aluminum. Due to increasing thermal conductivity as well as the surface area, the heat transfer from the hot surface to the cold liquid can be increased considerably. So the fin applications is generally the fins are used to transfer the heat from the source. Generally it may be electrical appliances or it may be the automatic sector to the surrounding air, that is called here air now. The fins are used when convective heat transfer coefficient is low to enhance the heat transfer rate. The second one is electrical applications like transformers and the motors engines like scooters, cars and motorcycle and compressors. The heat energy can be dissipated from the inside of the cylinder to outside air by keeping the fins. The engine cylinders of scooters, motorcycles, condensers and evaporators and refrigeration systems, car radiators, that heat energy is dissipated from the source to outside by keeping fins. These are the main applications of the fins. Here the main purpose is to enhance the increasing of heat transfer rate from the liquid surface to the surrounding air. The heat transfer through a fin of uniform cross section. Let us consider a fin which is kept perpendicular to the hard surface as shown in figure. This is representing the hard surface. Here it is known as here the fins. Let L be the length of the fin, which is kept perpendicular to the surface from which heat should be extracted, and width of the fin is represented W and thickness is represented by 2 alpha now. Let T naught is representing the temperature of the earth body, as in which is also equal to the temperature at the junction of fin as well as the vertical wall at this position. And the TA is representing the temperature of the surrounding air, that is the atmospheric air now. While deriving the quantity of heat that is dissipated by the fin, certain assumptions are also made now. They are, one is the flow of heat takes place under steady state conditions. That means the magnitude of heat flow per second, that is a uniform now. And it also takes place in only one direction, so that is along the length of the fin. The thermal conductivity of the fin material is always remains constant. The convective heat transfer H is uniform over the entire surface of the fin. The temperature TO at the base root of fin, that is at the junction of fin, as well as the wall, it is a T naught, which is also equal to the temperature of the surface, because the fin material is having high thermal conductivity. Okay, based on this assumptions, we are taking one problem on fin. A long rod, 12 mm square section, made up of low carbon steel, produced into air at 35 degrees centigrade from a furnace wall at 200 degrees centigrade. The convective heat transfer coefficient is estimated at 22 watts per meter square per degree Kelvin. The conductivity of the temperature will be 60 degrees centigrade. Also calculate the temperature at 80 mm from the base. The data are shown on figure number 1. For the long fin model, the equation can be written as now T minus A T alpha divided by TB minus T alpha. This equation is represented as e to the power of minus mx now. This equation is already derived in a previous video, which is equal to now, here 60 is representing here T equal to 60 degrees now, and 35 is the temperature of surrounding air, minus TB, that is the temperature of the source, that is the furnace, minus T alpha, it is equal to 35. From this relationship we got which is equal to e to the power of minus mx. So the distance x to be calculated by using this relationship, where m is equal to under root of hp divided by ka, where k is the thermal conductivity of the material, a the area of the cross section, and p is representing perimeter of the fin area, and h is the thermal conductivity of the fin now. From this relationship we got 22 into 4 into 0.012 divided by here now 519 into 0.012 into 0.12 now. This is another area of the cross section. It is another thermal conductivity. It is another perimeters multiplied by here 22 is representing the here heat coefficient of heat transfer for convection process. So on doing this calculations, we got m is equal to 11.89. So taking algorithm for solving the x values, for x is equal to 0.159, or we got which is equal to 159 mm now. So the temperature at 8 mm is given by equal to T minus 35 divided by 200 minus 35, which is equal to e to the power of minus mx. M already we determined it is equal to 11.89 into x is equal to given, it is equal to here 80 mm. From this relationship we got temperature is equal to 98.75. 4 now. So 98.74 is representing the temperature of the base at a distance of 80 mm from the intersection of fin as well as the vertical wall. So by using the data of problem number 1, this we are solving this one more problem. 2, here in problem number 1, if the length of the rod is 159 mm. In previous case, we have taken length of the rod is equal to 80 mm only. Determine the end temperature. Also find the temperature at 80 mm distance. All the data in problem number 1 are used as such, except the length is 159 mm. And the end is insulated or heat convected to the tip is negligible. The temperature distribution is given by the equation is equal to T minus T alpha divided by TB minus T alpha is equal to cos H into M L minus X divided by cos H M L. Where M is already we determined, that is the example, which is equal to 11.89. To find the temperature at a distance of X is equal to L now. Here from this relation we got to TL minus 35 divided by 200 minus 35, which is equal to 1 by cos H into 11.89 into 0.2159. From this relationship we got to, which is equal to 0.295 TL, which is equal to 83.272 degrees centigrade. The temperature at a distance of 80 mm is given by T minus 35 divided by 200 minus 35. It is equal to cos H. Here M is already we got to 11.89 into L minus X, where L is equal to length of the pin, which is equal to 159 already given now, minus of 0.08 divided by cos H 11.89 into 0.159. Just we have substituted the values of M as well as the X in this relationship. And doing the calculation, we got this values is equal to 0.24354 or T is equal to, from this relationship we got to 106.84 degree centigrade now. Here, problem number 3. A long rod 12 mm square section made up of low carbon steel produced into air at 35 degrees centigrade from the furnace wall at 200 degrees centigrade. The convective heat transfer coefficient is estimated 22 watts per meter square per degree Kelvin. The conductivity of the material is 59.9 watts per meter per degree Kelvin. Determine the location from the wall at which the temperature will be 60 degree centigrades. Consider the fin to be 80 mm long and the phase convections also exist. Determine the end temperature. This model is comes under here now, short columns. According to the relationship we got to T minus T alpha divided by TB minus T alpha. Already we derived these equations in the previous video, which is equal to cos H M into L minus X plus HL divided by Km into sin H M L minus X divided by cos H ML plus HL divided by Km into sin H ML. Where X is equal to L, this equation is reduced to TL minus 35 divided by 200 minus 35, because here this value is equal to now becoming 0 now, 1. Here, and substituting L is equal to 80, X is equal to 80, it is reduced to cos H 11.89 into 0.08 in denominator plus HL is equal to 22 divided by K is equal to thermal conductivity, which is equal to 11.89, sin H again 11.89 into 0.08. So from this relationship we got TL is equal to 143.1 degree centigrade. This is the temperature at the end of the fin of length is equal to 80 mm. If you plot the diagram for the three variations now, along the x-axis is the length of the fin, in vertical is the temperature at the root. Here 200 degrees centigrade is the temperature at the root, that is nothing but at the intersection of fin as well as the furnace surface. Here for the short films of 80 mm length, when we are considering for 80 mm length, for the short, it is having just maximum just 143 at end position now. If we take again, then 159, when the end is insulated means nothing but preventing heat from that particular surface insulated, or the heat transfer is from the end position is neglected or negligible. Then at the end position it is having 83 degrees, but at a distance of 80, that value is equal to 106 degrees centigrade. When the long pin is there now, that is the value at 80 is equal to 98 degrees centigrade, but at 159 its value is equal to 60 now. So the temperature is gradually dropping just when the length of the pin is increasing now. The Voigt number now. The heat conducted within the solid can be represented as here Q is equal to K into T1 minus T2 divided by here L we are taking now. This is the heat transfer from the one point within the solid to the other point in the same object, or between the two solids which are having contact with each other, where Q is representing the flow rate, that is the magnitude of heat that is transferred in, which is equal to K, that is known as thermal conductivity of the material, A is the area of the cross section, T1 is the initial temperature, and T2 is the temperature at the second point, where L is representing that is the distance between the 2 points at which the heat transfer is taking place now. Generally, it is called length. Sometimes it is also called the thickness of the wall, if it is a wall or any partition it is there. So this equation can be represented as now Q is equal to K into A into change in temperature is equal to delta T. S is representing that is the solid, that is the convection process divided by L now, where delta S is the temperature drop within the solid, that is T1 minus T2 value, and L is the already told thickness, K is thermal conductivity. The heat convected at the surface is given by Q is equal to HA delta T C now. So if the convection process is taking place, that is from the surface to the air or any liquid, it can be determined by using the relationship Q is equal to HA delta T C now. C is representing by using convection process now, where delta is representing the temperature drop or the temperature between the solid surface to the surrounding is the liquid, and A is representing the area of the section, surface area, here we are calling. H is representing coefficient of convective heat transfer. So equating these two, assume the heat is transmitting the same magnitude of heat is transmitting by using conduction process as well as the convection process. Hence these two equations are equal. Hence divide just one equation by other equations. That is, if it is the equation number 1, if it is the equation number 2, that is dividing equation number 1 by 2, we got delta Ts divided by delta C, which is equal to HL divided by K now. Okay, from this HL divided by K, it is known as the dimensional numbers. The dimensional quantity is named as Voigt number. If this number is small, then the delta will be small, and so the temperature difference between the 2 points within the solids or between the surface of the solid to the surrounding area very, very small. So it can be taken as a check for the applicability of lamp parameter model. This Voigt number is dimension less now. The quantity used in heat transfer calculations. It is defined as the ratio of thermal resistance within the solid body to the thermal resistance to the surface of the body. This formula here already we have taken now. Here in this case already given H is representing the convection heat transfer coefficient and LC is a characteristic length, typically defined as the ratio of volume of the body to the surface area now, where K is the thermal conductivity of the solid. This Biot number helps in understanding whether the temperature within the body can be assumed to be uniform, that means damped system analysis, or if the temperature gradients need to be considered. Generally, already I told it is used for damped system analysis. That is applicability of damped parameter model. So, interpretation based on the Biot number values. If the Biot number is very less than 1, the internal resistance to heat conduction is much smaller than the surface resistance to convective heat transfer. In this case, the temperature within the solid can be assumed to be uniform. If the Biot number is approximately, if it is equal to 1 now, both the internal and surface resistance are comparable and temperature gradient within the solid to be considered. The Biot number is greater than 1, the internal resistance to heat conduction is much larger than the surface resistance to convective heat transfer, indicating significant temperature gradient within the solid. The Biot number is less than 0.1. It has been proved that this model can be used without appreciable error, hence the model can be adopted. As this model is simpler to apply, it is worthwhile checking in all cases for the value of Biot number before attempting the solutions. Okay, this is the important of the Biot number. The second number is Fourier number. The Fourier number is again it is a dimensionless number like Biot number that characterized regarding heat conditions. But in previous cases, the Biot number it is related to the convection as well as the conduction heat transfer process. It is defined as the ratio of that is the Fourier number is defined as the ratio of heat conduction rate to the thermal energy storage. The Fourier number is commonly used in transient heat conduction problems to describe the temperature distributions within the solid over the time period. The formula for the Fourier's number is given by F naught is equal to alpha T divided by L square now, where alpha is representing the thermal diffusivity of the materials. Generally, it is measured in meters per second, and T is representing the time, which is measured in terms of seconds. L is equal to the characteristic length, which is generally it is ratio of volume of the material to the area of the cross section, that is V by AS. Here, the thermal diffusivity alpha is defined as alpha is equal to K divided by rho C P, where K is representing thermal conductivity of the materials, which is measured in terms of watts per meter per degree Kelvin. Rho is the density of the materials having units is equal to kg per meter cube, and Cp is representing specific heat capacity of the materials, which is measured in terms of joules per kg per degree Kelvin. The Fourier number helps to determine the time-dependent temperature distributions in a body. Here, some of the interpretations based on Fourier numbers are based on the value. If F naught, that is the Fourier number, if it is a very less than 1, heat has not penetrated deeply into the solid, and the temperature changes mostly conform to the surface only now. If F0 is equal to 1 now, the heat has penetrated significantly into the solid and the temperature change is noticeable through the solid. If F0 is very large, that means greater than 1 now, the solid is nearly in thermal equilibrium with the surroundings and the temperature is relatively uniform. These are the important of the Fourier numbers. Okay, these are the textbooks used for collecting the materials. Okay, thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.